what we will do today, we'll basically continue on the topic of the heterostructures, although they are slightly different. They're based on two-dimensional atomic crystals, which eventually should allow a little bit of more freedom in terms of the selection of the elements which can go into those heterostructures. So at the moment, most of those heterostructures are based or at least contain graphene. However, after 5 days of the conference, it will be probably too cynical to go into the introduction of graphene. So the only thing I want to say is that it's quite an amazing material obtained by such a humble technique and having such a simple crystallographic lattice. It allows for quite a variety of very exciting physical phenomena, both in transport, in optics, and also now in applications as well. So now I hope you would notice that if I show it like this, the picture is rather dull, and that's also what is noticed by our hyperactive students. They're all bright eyes, bushy tails, wants to expand a little bit more, always claiming and asking for, can we buy the other pencils as well, the colored pencils. And in principle, yes, some time ago it's been possible to obtain other pencils and other layered materials and try to exfoliate them as well. And we now basically can expand our range into other two-dimensional crystals because of the huge variety of layered materials which are available to us. Probably the most popular now is boron nitride. However, there is a whole family of dichocogonides there, some complex oxides, and in principle there are many, many more of those. So what we have now is basically is a family of those two-dimensional atomic crystals, and collectively this family covers quite a wide range of properties, from the most conductive to most insulating, from transparent to opaque, from mechanically strong to soft. And having such a library of those crystals would brings you to thinking, what if we can now stack them back into the three-dimensional stack again, however, not in a way nature intended it to be, but try to alternate them in sequence and try to bring some new physical properties and possibly some new applications from those stacks as well. So you probably have seen it several times on this conference already. I would just briefly say that it's a little bit of a painful job to do. How it is produced, it's all by hands, all done by mechanical exfoliation. Typically, you would create your two-dimensional atomic crystal on a double sacrificial layer, lift it up, flip it over, put it on another one, remove the sacrificial layer, do all the lithography contacts, whatever you want, and then repeat this procedure all over again. Generally, it takes, well, currently it's not unusual for us to have 6 or 7 transfers, 6 or 7 different layers of those materials, depending on the particular application you want to achieve. And it might take weeks to create even one sample. However, what is surprising is that the quality of those devices come out to be quite nice. Just to give you one example, if we, this sample is meant for drag experiments, as mentioned yesterday in a brilliant talk by Narozhny. So you basically have 2 layers of graphene in the shape of whole bars, and then if we now concentrate on a small part and basically try to carve away a small piece, a very narrow piece of this material, but basically just in a way it's shown here, and then if we mill it so thin that it can fit into the TEM, we can to take a look at it in the cross section, and that's our substrate silicon oxide, and the bottom boron nitride is over here, and then there is graphene, and then BN spacer, and then another layer of graphene there. And in principle, you can count all the layers, and with the EOS spectroscopy, you can even try to identify both of the graphenes there. Here is another example, just to flash a few nice pictures. Here is another example. It's slightly more elaborative structure. We started with underlying boron nitride, and then we placed a couple of, bilayer graphene, then bilayer boron nitride, and bilayer graphene, and then bilayer boron nitride, and then bilayer graphene again. It's, believe me, it's not just for the sake of a nice picture. That there was an idea behind this, what to do with this structure. It's all about resonant tunneling and negative differential conductance because you can open the gap in the bilayer graphene, though I'm not going to talk about it today. But what is surprising that if you, especially if you look at it in the dark field image, you basically won't be able to say where graphene starts and where the underlying boron nitride stops. So it's if you take all the precautions, the quality of those heterostructures can be quite amazing. So in the rest of my talk, I'll try to flash a few examples of what you can do with those heterostructures. And let me start with the simplest possible one, with the capacitor. And there are two reasons for that. One is that it's really the simplest possible heterostructure you can imagine. We basically start with underlying with the substrate with boron nitride, and we put graphene on top, and then a thin layer of boron nitride, depending on the particular experiments, say something above, for capacitance measurements, something above 5 layers of boron nitride would do, and then a top electrode on top, and basically you form a parallel plate capacitor between this plate and graphene. But the main reason is that the capacitance measurements gives you really deep insight into the physics, especially into the interaction physics in graphene. So if you measure the capacitance as a function of bias, surprisingly, well, it's not surprisingly, but the capacitance doesn't come constant. It shows this very pronounced, very sharp dip, and that's due to the quantum capacitance. It's well known that the total capacitance which you measure in such samples is given by the sequential geometrical capacitance and the quantum capacitance, and it's very easy to understand the origin of it. That's the simplified band diagram of a metal connected capacitively to our graphene through boron nitride barrier. And then imagine if you want to charge this capacitor, you take a probe charge from the metal to graphene. You have to overcome this electrostatic energy, that what gives you the geometrical capacitance, but also you have to pay this kinetic energy, or in some cases the interaction energy as well, and that gives you this quantum capacitance, which is simply proportional to the density of state in graphene. And of course, we all know that in graphene, the density of state vanishes at the Dirac point, at the compensation point, and then so this basically goes into infinity, and then it gives us this pronounced dip in the capacitance. You can understand it reasonably well with this linear dispersion relation, but also you can try to go a little bit beyond this, and it has been shown by several papers and also by several experiments as well, that this linear dispersion relation is always a simplified picture. It's only valid if you forget about interactions altogether. If you include interactions, then something very interesting happens. In any two-dimensional electron gas with parabolic dispersion relation, if you switch on the interaction, and if you load the carrier concentration low enough so the kinetic energy doesn't play much role, you would get into the Wigner crystallization. Of course, here it doesn't happen because kinetic energy and the potential energy scales are exactly the same way, square root of the carrier concentration. However, what happens is that the density of state gets this logarithmic corrections, and then it's basically diverges close to the Dirac point, and in principle you can try to feed the same data by including these electron-electron interactions, and well, you won't see much difference on this scale. However, if you recalculate those data to extract the Fermi velocity, basically the slope of this density of state, then you would get that the Fermi velocity is not constant at all. You cannot fit it with that green curve, which assumes linear dispersion relation, constant Fermi velocity, but this logarithmic diversion fits the data really nicely. Now we can go to the magnetic field, and of course you can expect much more from the measurements of the compressibility in magnetic field, because your spectra splits into those Landau levels, and you see this standard fun diagram for all the Landau energy levels. The standard sequence -6, -2, 2, 6, 10, and so on are those thick lines. So it's basically every time the Fermi level gets into the low density of state, means into the gap, we see a dip in the capacitance, and then if we concentrate, say, on this area, what you see that also the other the degeneracy, the fourfold degeneracy, which you expect generally in graphene, 2 comes from spin, 2 comes from the valley, is also lifted. You see this -1, 0, 1, and in fact 3, 4, 5, and then 7, 8, 8, 9 as well. So all the degeneracy is completely lifted, but also those faint lines, they're coming from the fractions, and so we heard a very nice talk yesterday on the fractional quantum Hall effect in graphene by Jürgen Smet. In contrast to his talk, to his samples, what we actually do see the 5-third fraction, which might be quite puzzling. So I'm not going to talk about the fractions in graphene. Jürgen Smet covered it fantastically well yesterday. So what I'm going what I want to bring your attention to is that this, say, state 1/2 here, the states around 1/2, 3/2, and so on, are much brighter than the rest of the picture. And what it means that the capacitance goes above the geometrical capacitance. So if I plot this, the same plot at 0 magnetic field, we have this pronounced dip when the density of state vanishes, so the capacitance should go to 0. However, if the density of state goes up, the capacitance, so this term doesn't play much role anymore, and basically the capacitance should go to its geometrical limit. Now it's even more prominent in magnetic field, because of course you have a huge density of state if you are sitting exactly at the Landau level, and then this line here gives you exactly the geometrical capacitance. Now if you go to the higher magnetic field, what you would notice that at around 1/2, 3/2, and so on, you would see that the value of the capacitance goes above the geometrical term, and it means that our compressibility is negative, which can be expected if you allow for interaction effects like Wigner crystallization, for example, in graphene. Of course, in magnetic field, it is possible because you quench the kinetic energy completely. However, there might be some other effects as well, like, for example, excitonic excitonic effects due to interaction with the nearby gate, and there is quite a few of very exciting physics there. So I want to stop here on the capacitance and move to my next topic, which will be on the Morass structures. And for some time, people have been really excited about this graphene on boron nitride story, because everybody thought that's the perfect substrate for graphene. It doesn't give you much of the interaction, so that's where you see the bare graphene. And apparently, it's not entirely so. If you put graphene on top of boron nitride, what you see is this Morass pattern, which is there simply due to the fact that the lattice constants of the two crystals are different by 1.8%, and in principle, it's not only the geometrical effect, you can actually see it experimentally as well. So in STM experiments, you can see it quite nicely. However, the period of this Morass, so those are not atoms; the atoms are on much finer scale. You can just about see them there. So that's the Morass structure, and this Morass pattern got very different. Very different period, simply because it depends very much on the angle of rotation between the two lattices. And this nice period of say 14 nanometer, if you align the two crystals perfectly, can be seen only in a very narrow range of the angles between the two crystals. And then as you misorient, you go very, very fast into very low periods of the Morass structure. Now, of course, it doesn't seen only on. You can see it also in electronic properties as well. Here is the scanning tunneling spectroscopy picture, and you can see a very pronounced one-half singularity followed by a sharp minimum in the density of state, and that's in principle what has been expected. Quite a few papers there, and there was a very nice talk yesterday by Martin, and you can expect some sort of spectrum reconstruction at the Fermi vector, which is given by this wavelengths of the Morass pattern, and the question is, can we observe it in transport experiments as well? It should be possible. However, the only problem is that generally it is offset into quite high energy, so you need lots of doping to get into those energies. And then if you put all the numbers right, basically you would find that the range of the periods of the Morass pattern which allow you the observation of the spectrum reconstruction in transport, you basically need to bring it within, say, 300 MeV to the Dirac point, otherwise you won't be able to dope it. And the range of those wavelengths is quite narrow, so you basically need. I mean, the wavelengths are of course large, but the angles which allows you to see it are only plus minus 2 degrees of the misorientation between the two lattices. So if you leave it completely by chance, you would be very unlikely to observe this effect at all. So to that respect, what we've done is we're very careful at our selection of the crystals which we use in our experiment. For example, here is a crystal of boron nitride, and it's been noticed for quite a long time now that usually those mechanically exfoliated crystals would always have nice facets, and then those facets are always lying under 60 degrees to each other, and then half of them would correspond to armchair edge, half of them correspond to the zigzag edge. And now when you do all the transfers and arrangement of those heterostructure, if you take some care about aligning of the crystals, so here is the, I'm not sure if you can see it actually. So this white bit is exactly this one, and then on top of that, So that's graphene, that's bilayer graphene, and then what we did here is we aligned the facets of boron nitride with the facets of graphene, and then of course we don't know which one is which one is zigzag with which one is armchair, but at least you have 50-50 chance now to align the two crystals perfectly. And then, so in this case we were lucky, and that's the conductive IFM image of the Morass pattern of graphene on boron nitride, and you can see that the period is roughly is very close to the 14 nanometers, which means that the misorientation is within half a degree. So if you do the transport on those properties, if you stay within low carrier concentration, just within here, you won't distinguish it from normal graphene at all. It's the same peak in the resistance, change of the type of the carrier concentration if you go from electrons to holes. However, if you go to higher carrier concentrations, you would see a small peak in the resistance and on the electron side. But what is more important is the change of the sign of the RXY simultaneously with this peak, and this peak is much more pronounced on the whole side. It's actually much larger than the main Dirac peak here. And then again we see the change of the type of the charge carrier. So it's quite an exciting story. Now what we basically do, we start with very well into whole conductivity here, so just our transport is dominated by holes, and then suddenly RXY changes the sign. It means that we now have electrons which carry charge, and then we get into into whole conductivity again. The temperature dependence of those guys is quite different. I'm not going to go into details there, but it basically allows you to say something about the degeneracy and the Fermi velocity of those new Dirac points. So we basically see it as a new generation of Dirac quasi-particles, new cones there, and as you've seen yesterday from Martin's talk, you can, depending on the type of the interaction, there might be one or three or cones there, and in our experiments we would say that it's most probably one cone, one new generation of Dirac quasi-particles now. It's more interesting, of course, in magnetic fields. So here you see the standard Fund diagram from the Landau levels, which are coming from the main Dirac cones. That's with the standard 4 sequence of the Landau levels. But then there are this filling factor 2 sequence which is coming from the secondary Dirac fermions. From here, it's not really a quantum Hall effect for the secondary Dirac fermions, because we are in ultra quantum limit already at about 3 Tesla. Basically, all those, if we are sitting in this state, we already pin the Landau level to the 1/2 singularity at the edges of those little cones, and it's basically we interact with the Landau levels which are coming from the main Dirac point. Similar story is on the electron side. It's just slightly less pronounced, and the exact arrangement of the filling factors which are seen depends a little bit on the sample preparation. Now I won't talk too much about this. Just say that the exciting story comes if you plot RXY, and what is important here is that if you say sit at this point and you start with electrons here, and then you change magnetic field. You don't change the carrier concentration. You fix the carrier concentration by gate, but then you change the carrier concentration, and your color here oscillates from red to blue to red to blue to red to blue, and so on. And it basically means that the magnetic field alone change the type of the carriers which you see in your experiment. Change electrons to holes, and it changes periodically with and then along certain values of the magnetic field, and then in sigma XX we see those minima in sigma XX simultaneously with the RXY changing sign. So it basically can be interpreted as new neutrality points and as new generations of quasi-particles. Now it is the third generation of the neutrality points and the third generation of the Dirac fermions, and it can be also interpreted. Well, you get a little bit better insight if you plot it not as a function of magnetic field, but as a function of the phi naught over phi, where phi is the flux through a sample, and basically you would notice that that's just another sample. You notice that every time your flux fits into the integer number of the plaquettes of those Morass pattern plaquettes, you see these changes in the sign of the RXY, and then that's where you see the new generation of the quasi-particle. An alternative way, of course, is to say that it's basically a point where you can renormalize your magnetic field, and you basically change the new magnetic field changes sign at those points. So now you're working in effective magnetic field B minus B naught, and B naught is basically given by the flux quanta going through the integer number of those plaquettes. So the whole story, of course, resembles the famous Hofstadter butterfly, which has been studied quite intensively in the lateral sublattices in gallium arsenide by Dieter Weiss, and however, those experiments, well, you could see only small glimpses of those of the Hofstadter butterfly, and also those experiments have been done in a different regime of a weak interaction, where you basically all you do is the broadening of the Landau levels of the massive Dirac fermions. It's very different here. We are in a strong interacting regime. Those are the calculations from the Lancaster and Bath groups now, and you can see that the Landau levels from the main Dirac point interact with the Landau levels from the secondary Dirac point, and then you have all those at the crossing points. You have this new generation of the quasi-particles. If I zoom up here, you basically see that the Landau levels here, they very much resemble the Landau levels coming from the main Dirac point. It basically can be interpreted as the new generation of the Dirac fermions, just in effective magnetic field. I just to flash that it fits reasonably well with the experiment, even though the two axes are not exactly the same. But there are probably more questions than answers in this story, and there will be quite a few developments there. And I won't say much more here, and then I'll move to my next topic, which is more on the application side now of those heterostructures rather than on the physics side. So let's now, if you remember this stack, let's make this stack a little bit more complicated, more interesting. We get into the two layers of graphene, which are separated by a monolayer of boron nitride. And it's the same story as for the drag experiment, which we discussed yesterday. Just for drag experiment, you probably would try to use a little bit thicker spacer here, because one layer of boron nitride is too thin, and it allows lots of tunneling between the two graphene. In fact, it's the tunneling rate is quite large. You basically get roughly 1 kilo ohm pure square micron of the resistance for such a structure. However, of course, you will have full control on it, and we can put, say, 2 layers of boron nitride, and we get into tens of kilo ohms of the resistance, or 3 layers, or 4 layers if you want, and then you basically get into the proper tunneling regime with about 1 gigaohm of the resistance, and it scales quite nicely, exponentially with the thickness of this boron nitride. So we feel that we understand this tunneling quite well. The IVs, however, they do not scale with they do not scale exponentially at all, and the reason for that is that your tunneling current is generally dependent on the transmission probability, but also on the density of states of the emitter and the collector. And here we used boron nitride with the gap of 6 eV, which is much larger than the Fermi energy which we can induce in graphene. So the tunneling probability doesn't change much, and all we do, we change the density of state in the two graphene, and that's why the tunneling current changes. Now, but this density of state, of course, can be also changed externally, for example, with a gate. And then what happens if we don't apply any gate? We tunnel from one Dirac point to another Dirac point, and of course, the density of state is 0, so we pretty much don't have any tunneling at all. And or we can apply, say, some finite gate voltage, so we induce electrons into both of the graphene layers, and then the density of state increases dramatically, and we immediately have very high tunneling current. And of course, we can feed it, put all the other gate voltages there as well. So basically what we have here is a tunneling transistor with the external gate voltage, which we can control the tunneling current through this boron nitride barrier. Well, it's not very good tunneling transistor. The gate dependence gives you only the on-off ratio is roughly 50. However, it's already better than but that's at room temperature. However, it's already better than the tunneling transistors which have been proposed from gallium arsenide, say 20 years ago. Let me now just make a little bit of a break and just kind of provide a halfway entertainment here. The boron nitride is, of course, very nice material, and it's very clean, and we like to work with it. But however, if you want to use it as a tunneling barrier, you can use any other material as long as it is of reasonable quality and it is it is flat enough and can be made thin enough. And here we used this material, vermiculite, or it's basically clay, to be used as a tunneling barrier. And one reason to use exactly that material, that it is readily available from any shop. It's basically something which goes into the filler of the cat litter boxes. You can exfoliate this vermiculite quite readily. You can put it into as a barrier into your transistors, and it does work. You control the tunneling current with external gate. It's not very good transistor. The on-off ratio is really miserable. But what is nice there, that some of those vermiculites, they are piezoelectric material, so you can see the switchings in the tunneling current, so you can probably use it as a kind of memory device. But that's more as an entertainment, really. So if you really want to use it as a transistor, what you need to do is to find a material with very small gap. So the size of the gap would be comparable to the changes of the Fermi level, which you can induce in your graphene. So in this case, the tunneling probability would be changing as well, and it goes exponentially with the height of the barrier. So, you would be dominated not by the density of state, by the exponential changes in the tunneling probability. And one of those materials, well, actually, quite a few of those materials are available. It's the transition metal dichalcogenides, for example, molybdenum disulfide is one of them, and it's known that depending on the thickness, the gap there goes from 1.9 to 1. In monolayer to 1.3 in the bulk, and it really fits us perfectly because we can basically get half a V of the changes in the Fermi energy. So that's one of those transistors. Looks horrible, but the most important part is there. So there are a few layers of moly sandwiched between two graphenes, and then everything is coupled is kept by BN, and there are a few of the service layers as well. And it does work well if you apply, say, negative gate voltage, then your barrier is extremely high and you don't see much of the current. However, if you apply positive voltage, you get into the you bring the Fermi level close to the bottom of the conductance band in moly, and you see a very high current, and basically in the good transistors you can obtain on-off ratio of about 10⁶, which is already close to what is required on the commercial scale. Let me now just I have a few minutes, 5 minutes. Let me now just very briefly mention what happens if you shine light on those transistors. So in principle, what should happen? We basically, the system is very, very similar to the double layer of gallium arsenide, and you can excite electron hole pairs either in graphene itself or in the barrier. The problem is that, of course, if there is no built-in electric field, these electron hole pairs will simply recombine, and you won't see nothing. So another problem is, of course, boron nitride is not an ideal material at all. It has the gap of 6 eV, so it's not very practical for either applications or to work with it. So the first problem is quite easily resolved by applying some gate voltage, because by applying gate voltage you can induce built-in electric field, and now if you excite an electron hole pair here, it basically will decay into the opposite electrons, because it will be split in this built-in electric field. So you should be able to see some photocurrent, and then you can also, as I showed you can use moly or tungsten disulfide as a material with much smaller band gap, and also here you benefit from the fact that the work function of graphene fits quite nicely to the work function of either of them, either moly or tungsten disulfide. So the Dirac point sits somewhere in the middle of the gap, and details depend on the doping, really. But it basically can work as either hole acceptor or electron acceptor. So that's the type of samples which we work. Again, very complicated. You won't see much because there are plenty of service layers there as well. But the most important part is that the graphene is there at the background, and tungsten disulfide is here, and then there is a top graphene on the top. And what we do, we basically scan with a laser across this structure and look at the photocurrent response measured between those two electrodes, and you do see indeed some response. Well, not very much here, but this response is only at the area where the 3 layers overlap. So it means that the mechanism which we are thinking about is indeed correct. And now, of course, what you can do, you can apply gate voltage, and you basically induce this electric field, this built-in electric field, and you immediately see a huge increase in the response, in the photovoltaic response of this structure, or you can change the polarity of the gate voltage. So you change the polarity of the built-in electric field, and the photocurrent change sign, of course, simultaneously. It's not a very good device if you have to apply the gate voltage all the time. You can go for alternative routes. You can, for example, dope one of the graphene layers differently to another one, which also introduces the difference in the work function and the difference in the and gives this built-in electric field, and then it basically shifts the whole picture to the right, just giving some finite response even at zero gate voltage. So surprisingly, I mean, originally we just played with it a little bit, but surprisingly, it's the quantum efficiency of those devices is quite good. So that device is not optimized at all, and the quantum efficiency is the external quantum efficiency is already 30%, which is quite an appreciable number, especially considering that we have extremely thin layer of molybdenum disulfide there, only say 3-4 layers, so it's quite transparent. It doesn't absorb much light at all. So, however, if you really want to use it for something practical, you might want to improve the absorption probability in the layer of transition metal dichalcogenides. One way is to make it thicker, which is not really practical because you spread this built-in electric field along the longer distances. But another one is really to benefit from the plasmonic story of and say put some plasmonic structure, and the simplest one is simply droplets of gold on the surface, which absorb all the light and create the evanescent field exactly where we need it in the area of transition metal dichalcogenides, and then you basically can absorb much more light, and the efficiency increases dramatically. And here we have an example of a bad device with not much of the photoresponse. However, as you put the plasmonic nanostructure, the photoresponse increases, and notice the tenfold increase in the scale here as well. And I'll probably finish here, and I should say that there are plenty of excitement both on the application side and on transistors and photovoltaic devices, but the physics is probably even more interesting. The Hofstadter story is going to be to develop quite a lot now. That's probably one of the major direction of research for our group. And let me thank my collaborators, especially Andrew Gaim, and the 4 topics which I covered today are mainly by Roman, Liam, Gillian, and Artyom. Thank you so much.
Thank you very much for a fascinating talk. We have some questions, and here is one right here.
So, Kostya, you showed at the same time the renormalization of the velocity by interactions, and at the same time Hofstadter butterfly, which is understood as on the basis of non-interacting system, and you have to have a lot of really very strong interferences to get this self-similar spectrum. So could you maybe comment on what would be, how this is possible?
Right. So the real issue is that we now understand only the broad picture of this Hofstadter butterfly, because all the samples which we produce, they're slightly different one from another. There are some self-similarities between them, and those which I covered here, that you always have this switching between electrons and holes at the phi node over phi at being integer and so on. However, there are small details like even the degeneracy of this secondary Dirac cones is not really well understood at the moment, and that might depend on the particular arrangement of between BN and graphene, but that's not even the interaction story yet. Now, as you said, there is an interaction story, and at the moment I cannot even predict what's going to happen with the interaction.
Thank you. Other questions, comments? Yes, please.
Generally speaking, in order to make a good a photovoltaic device, the requirements are more or less the same as making a good light emitting device. Have you done any experiments on light emission from your graphene molybdenum disulfide structures?
Right. That's in principle that's correct. However, of course we are working on that. The problem is that our moly or tungsten disulfide they're quite thin, so the lifetime of electrons in it are quite small, because it's quite a transparent device. However, there are, if you go to, how do I do it? If you go to the first few layers, so I'm not sure if I have it here, but basically, if you make a structure something like this, tunnel from graphene through boron nitride into tungsten disulfide, and then through another barrier into graphene somewhere there, if you basically manage to keep electrons inside of this barrier for long enough time, so it would be the lifetime in the barrier would be longer than the life emitting time, than the photon emission time, then yes, you would get the light emission properties there as well. We do work on that, so that's why we basically need more than, say, 5 or 6 layers simultaneously in the device, because basically what you're trying to do is to make the profile of the barrier not trivial, not just a simple flat barrier, but you need some structure to trap electrons inside. Yes, people are working on that.
Thank you. Are there other questions or comments? There's one up there.
It's concerning the last part that you mentioned about the structure and the quantum efficiency that is very high at low power intensity, laser intensity. So why is that?
I don't know. I can only speculate. So, indeed, the quantum efficiency changes with the power, and it goes down with the power. One of the possibility is that you photoexcite so many carriers that they start to screen the built-in electric field, and basically the central part of your barrier doesn't work anymore. And the more photocarriers you get, the more of the screening of this field you have to take into account. So you are only in the linear regime at the lower excitations.
Okay. Wouldn't these photocarriers go to your electrodes and your detection system?
Sorry?
Wouldn't these photocarriers go to the detection system? They want to stay there screening, or would they?
Wouldn't this photocurrent go into
the detection system? You're collecting electrons.
Yes.
So these excited electrons, photoelectrons, will go directly to the detection system. So they wouldn't stay there screening the photons.
I mean, it still takes time to tunnel from one layer to another. It takes it still takes a few microseconds probably, because the hopping between the layers is quite weak. So you have to take into account the hopping time.
Okay. There are other urgent questions or comments? If not, we will thank both speakers for a very, very nice talk.